Hello everyone, welcome to EPG Pashala. My name is Dr. Roshan Livingston, working as a medical physicist in the Department of Radiology, Christian Medical College, Vellore. The module that we are going to see today is about fluoroscopy. This module comes under the paper on radiation biophysics. What is fluoroscopy? Where is the origin of fluoroscopy? The origin of fluoroscopy can be traced back to 8th November 1895 when Wilhelm Conrad Röntgen noticed a barium platinocyanide screen fluorescing as a result of being exposed to X-rays. Fluoroscopy is a radiological examination which uses X-rays and a fluorescent screen or a detector to visualize the internal structures of the body in real time. So we are going to see the objectives of fluoroscopy in this module. The objectives are to understand the principle of conventional fluoroscopy, to understand the fluoroscopic imaging chain, understand how fluoroscopic images can be acquired using image intensifiers, understand types of fluoroscopic equipment used in a hospital. Now, what is fluorescence? We were talking about fluoroscopic imaging machine, so we need to know about fluorescence. Fluorescence is a phenomenon where certain materials emits visible light in response to some stimuli. The stimuli can be X-rays or electromagnetic rays, and the emitted light that is coming out from this material stops soon after the stimuli is stopped. In this small picture, you will be able to see light emission from a fluorescent screen in an early fluoroscopy machine. Conventional fluoroscopy. This was used for over more than 100 years. So when X-rays pass through a patient, they are attenuated by different internal structures of the body and cast a shadow of the structures on the fluorescent screen. In this photograph, we can see a radiologist imaging a lady who is probably swallowing barium and is seeing the internal structures of the body with the help of an X-ray machine as well as a fluorescent screen. Here this illustration also you can see X-ray tube, a couch where a patient can be lying down, and then there is a fluorescent screen. On top of it is a lead glass. The earlier conventional fluoroscopy machines had dim fluoroscopic images, and that requires dark environment. So eyes have to get adapted to dark environment. So when you go into a fluoroscopic room, the entire room is switched off, all the lights are switched off. Finally, the eyes get adapted to this dark environment. It takes about 5 minutes. After that, we see this dim image of a fluoroscopic image as seen in this image. A thin lead glass is placed behind the fluorescent screen for radiation protection purpose. So what is the advantage of this conventional fluoroscopy? Is its simplicity and cost effectiveness. The disadvantage is it can impart high radiation dose to the patient as well as others who are there in the room. To visualize the image, one has to stand on the path of the primary beam. And the problem is it requires feebly illuminated room and requires dark adaptation. Next, we move on to a fluoroscopic imaging chain, which is part of our objective. Till now, we learnt about how a conventional fluoroscopy works. But in case of image intensifiers were introduced in the year 1950s. It allows fluoroscopic images to be visible under normal lighting condition. So what are the components of this fluoroscopic imaging chain? From this illustration, you can see it has a generator, X-ray tube, collimator, filtration, a table for the patient, and the patient, grid, image intensifier, optical coupling, video camera, and a monitor finally to visualize the image. Let's go step by step on this fluoroscopic imaging chain. The X-ray generator. The work of the X-ray generator is to enable selection of kilovoltage and tube current, that is kV and mA, for the X-ray tube. The kV and mA can be altered using automatic brightness control. It's called ABC. Now, why do we need an automatic brightness control? It maintains the overall image brightness at a constant level as the image intensifier is spanned across different parts of the body. Next, we move on to the X-ray tube. It requires high tube loading for extended use because fluoroscopy is a continuous process. It's not like the exposures which are taken in routine radiography. It can have a grid control X-ray tube for instant switching between exposures. It may have about 3 focal spots for improved image resolution. It can have fixed fluoroscopic machines with rotating anode X-ray tube, but mostly the small C-arm machines have stationary anode X-ray tube. In fixed machines, their X-ray tube rating is up to 1100 mA. In mobile machines with a stationary anode X-ray tube, the rating is about 8 to 11 mA as seen in the image. The next component of the fluoroscopic imaging chain is the collimator. The collimator is similar to the radiographic imaging machine, but except it has something called the iris, similar to what we see in a digital camera or an old manual camera. It is a device used to limit the X-ray beam falling on the patient. It contains of multiple sets of radiopaque shutters which can be made of lead. Proper use of this collimator can reduce scatter as well as improves image quality. After that, we have the filters. The work of the filter is to reduce the low energy X-rays that can be absorbed by the patient tissue without being transmitted to the detectors. Aluminum or copper is commonly used as an added filtration material. Patient table. Patient table provides adequate strength to support large patients as well as result in minimal X-ray attenuation. Carbon fiber composite material is generally used as a patient table, which has about 0.5 to 0.75 aluminum equivalents. Grid. Grid is used to reduce the scatter from the patient which is reaching the detector, and which also improves image contrast. The use of grid increases radiation exposure. In fluoroscopy systems, the grid ratios range from 6:1 to 10:1. But during pediatric cases, to remove grids while imaging pediatrics and thin patients. In fluoroscopy system, the grid ratios range from 6:1 to 10:1. It is good to remove grids while imaging pediatrics and thin patients. We then move to image intensifier. The function of the image intensifier is to convert incident X-rays into visible light image to be viewed using monitors. It just resembles an old fluoroscopic screen. But however, this image that was converted to light has to be converted into electrons so that you are going to get a digital image. What are the main components of this image intensifier? It has an input phosphor and a photocathode, electrostatic focusing lens, an accelerating anode, output phosphor. These are the main components. From this figure, we see various types of image intensifier tube that are generally used for ceiling mounted or floor mounted fluoroscopy systems. Small image intensifier tube or II tubes are used in C-arm machines. C-arm machines are used in the operation theatre. Let's go ahead with the II machine. The input layer, as you see in the image, it has an input window, a substrate, input phosphor, and a photocathode. The input window is curved in shape with a layer of metal or glass. When X-rays pass through the input window and the aluminum substrate, it reaches the input phosphor. The input phosphor is made out of cesium iodide crystals, or other cases gadolinium oxysulfide. The function of these crystals is to convert X-ray pattern into a visible light pattern. The photocathode is a thin layer of antimony and an alkali metal. The function of this photocathode is to emit electrons when struck by visible light produced by the input phosphor. So when X-rays fall on the input phosphor, it gets converted into light, and the light gets converted into electrons with the use of a photocathode. Then we have the electrostatic focusing lens. A potential of about 25 to 35 kilovolt is applied in the electrode, and an anode plate is placed inside the glass envelope. The electrodes focus the electron beam from the photocathode towards the output phosphor, because electrons can be accelerated by electrical and magnetic field. The electrostatic focusing lens inverts and reverses the image on their way to the output phosphor as seen in the image. The energy of each electron is substantially increased and gives rise to something called the electronic gain. Now the output phosphor, what is it made out of? Output phosphor is made of zinc cadmium sulfide doped with silver, and it emits green light. This converts the electron pattern into bright light pattern. The diameter of this output phosphor ranges from 0.5 to 1 inch. Then we move on to an optical coupling. Till now what we saw was the input phosphor converts X-rays to light. The photocathode converts light into electrons. Electrostatic focusing lens will attract these electrons towards the output phosphor, and finally the output phosphor converts the electronic image into a light pattern. This light pattern should be captured using optical coupling. The optical coupling is similar to what we see on a lens, which is used for our cameras. It consists of lens assembly to couple the video camera to the output of the image intensifier. The lenses focus the incoming light from output phosphor onto a focal plane of the camera. There is a small aperture in the lens assembly which varies the proportion of light entering the video camera. This is how a video camera looks like. It is a Vidicon camera which uses semiconductor material such as amorphous selenium, which is sensitive to the intensity of light falling on it. Let us consider how the camera captures the image. The optical image formed in the output phosphor of the image intensifier is focused on the signal plate of the camera as seen in the illustration. Conductivity of the corresponding point on the target in the signal plate is altered because there is a impinging of light photons onto the selenium plate of the camera. The electron gun present in the camera gives out a narrow beam of electrons. The electron beam scans the target using accelerating anodes A1 and A2 and the deflecting coils C1 and C2 as shown in the figure, and converts the electrons in the image into current flowing through the resistor R connected to the external circuit. This camera produces a signal voltage which can be amplified and fed into the television monitor for viewing. There is an illustration which is seen in the image, a fluoroscopic image from barium swallow procedure. Fluoroscopic equipment. Fluoroscopic equipment may have image intensifiers, or the recent ones have flat panel detectors for real-time imaging. It can be equipped with either an undercouch or an overcouch X-ray tube. Mobile C-arm. What do we see in a mobile C-arm? The mobile C-arm is used in operation theatre for orthopedic and urological surgeries. That's how a mobile C-arm looks like. We have seen the image intensifier on top and the X-ray tube below. That's called an undercouch X-ray tube C-arm machine. This kind of machines are usually having stationary anode X-ray tube and can be used for orthopedic and urological surgeries. Some of these cases where there is a fixed X-ray tube, fixed fluoroscopic equipment, as seen in this image, it has an X-ray tube on top, hence it is called an overcouch X-ray tube, and there is a table where a patient can lie down, and underneath that table is the image intensifier. It is generally used for performing gastrointestinal and genitourinary procedures. One such example we see here is barium swallow procedure and a barium enema procedure. The undercouch X-ray tube machines are available in angiography suits, which can be used for cardiology purpose or radiological interventions. This has higher tube rating, and the size of the image intensifier can range from 12 to 16 inches, so that the entire abdomen can be covered. Due to its high tube loading of X-ray tube, it has high heat units. So separate assembly for heat units, so separate assembly for cooling the X-ray tube is required in such machines. It is used for cardiological and radiographic interventions. Cardiological procedures such as percutaneous transluminal coronary angioplasty or cerebral angiographies, which are done in radiology department. The angiographic machines, which are used for radiological purposes, for interventions or cardiological procedures involve higher MA tube. Hence, procedures such as cerebral angiography, cerebral interventions, other cath lab procedures can be performed in this. When we enter into the operation theatres, we may see a fluoroscopic C-arm. These are small C-arms of the order of 8 MA to 11 MA. The options available as seen in this module is an image rotate, where one can rotate the image. Also, we can image reverse, or we can reverse the image, and we have the acquired images to be saved and to be sent to the picture archival communication system. There are also magnification modes in these machines. In some machines, there may be about 6 magnification views, but in the smaller machines, there may be 2 magnification modes. However, one should justify the use of magnification mode. Use of magnification mode increases the radiation dose imparted to the patient. Now, there is also a collimator. You can either open the collimator wide or collimate it tightly. If we collimate the image tightly, the images have better contrast, as well as the scatter to the operators is reduced. We see here the iris of that collimator, as well as some wedge filters are available to have uniform intensity in the X-rays, so that our image has uniform intensity. There is also manual contrast. What we see here, there can be an auto contrast, which can be set according to the automatic brightness control, and also in case we need to have separate images onto a film or onto a CR plate, we can have KVP separately and MAS, and certain images can be acquired. For fluoroscopy mode, we have pulsed or continuous fluoroscopy mode. In the pulsed mode, radiation dose can be reduced compared to the continuous mode. Pulse modes vary from 0.5 to 15 or 30 frame rates or pulse per second. There is also low dose option. For an Indian patient, it is always good to use low dose, and it depends on the patient's habitus. There is also a 5-minute alarm reset button. This is an integrated timer to warn the interventionist or the orthopedic surgeon regarding high doses going to the patient. Some of the safety checklists in fluoroscopy is to obtain patient history about previous radiation exposure, ensure operators and personnel wear well fitted lead aprons, thyroid shields and protective eyewear, position hanging table shields and overhead shields prior to the procedure. In some cases, use ultrasound imaging when possible. Position the detector, which is the II, as close to the patient as possible. For C-arm type fluoroscopic units, maximize the distance from the radiation source. Use the exposure pedal sparingly. Use pulsed rather than continuous fluoroscopic mode whenever possible, so that we have low doses imparted to the patient. When low doses are imparted to the patient, it will also reduce the radiation dose scattered to the operators. Review and save anatomy with the last image hold rather than with live fluoroscopy whenever possible. Position and collimate with fluoroscopy off, tapping on the pedal to check position. Collimate tightly, exclude eyes, thyroid, breast and gonads when possible. Minimize the use of electronic magnification. Use digital zoom whenever possible. Adjust acquisition parameters to achieve lowest dose necessary to accomplish procedure. Use lowest dose protocol possible for patient size, lower frame rate, minimize magnification, reduce length of run. Operator and personnel hand should be out of the beam. In case of using power injector or extension tubing, if hand injecting, be careful to synchronize the power injector while the images are taken. Move the personnel away from the table or behind protective shields during acquisition. Minimize overlap of field on subsequent acquisitions. Plan and communicate in advance the number and timing of acquisitions, contrast parameters, patient positioning, suspension of respiration with radiology and sedation team to minimize improper or unneeded runs. Acknowledge fluoroscopic timing alerts during procedure, such as the integrated timer. After procedure, record and review the dose. Ensure appropriate monitoring of dosimeters. Arrange for appropriate follow-up and discharge instruction for high dose procedures. I hope you understood a little bit of what fluoroscopy is all about. We talked about conventional fluoroscopy and image intensifier. What is fluoroscopy? It is a radiological examination. Let's summarize. Fluoroscopy is a radiological examination which uses X-rays and a fluorescent screen or a detector to visualize the dynamic process within the body in real time. Fluorescence is a principle where certain materials emit light, that is visible light, in response to X-rays, and the emitted light stops as soon as the stimuli is stopped. Dark adaptation is required while visualizing images in conventional fluoroscopy system. Image intensifier instead of the fluoroscopic conventional machine. Here we have image intensifier which converts incident X-rays into a minified visible light image and amplifies the image brightness for better visibility to the viewer. Adequate care should be taken while working with fluoroscopic devices, as it involves high radiation dose to patients and staff. I hope you enjoyed watching the fluoroscopic module. Thank you.